Good morning, Physics C. This will be the Ampere's Law magnetic field lecture. We've already covered magnetic field is mu naught I over 2 pi r. We saw the form take shape in lab, and then we briefly looked at the law of Biot-Savart, which is really the building block for what we care about, mu naught I over 2 pi d. We're going to take a closer look at why that quantifies the magnetic field intensity a known distance away from a current carrying wire. This is a shorter lecture with some, thinking back to some math skills. And then the only thing we do after this with magnetic fields is we then take the knowledge we learned in the first lecture and this lecture and apply it to solenoids, which would be the technology employed by, say, an MRI machine, and really any electromagnet you have ever used, knowingly or unknowingly. And then we move to magnetic force, which is the back half of chapter 32. So, so this is like anything we do. It's going to be thoughtful, but thought-provoking and a little challenging, but we can totally do this. All right, there goes my face. I'm going to bring the pointer up. Let's do this. All right. First, a mathematical aside on a line integral. When I go for a hike in the woods, here's the path. And how long is that path? Well, if each of these represents 1/10 of a mile, and I call that delta S, if I count those up, it looks like from start to finish, it looks like the path is about a mile long because there's 10 chunks. I just did a line integral. Okay, now that sounds all fanciness, but really you see it's not that fancy. Okay, if I wanted to go mathematically, what I say is I would take the sum of all those chunks, and if those chunks happen to be infinitesimally small, I might say I'm taking the integral from start to finish of all those ds's, infinitesimally small chunks. Okay, I can think about how I might apply that to magnetic fields. This slide is going to be a little voodoo abstract. I struggle to articulate it in words. The next slides are going to make it way more plain English, but let me give this a shot. When you think back to calculating work, and I mean in the most basic sense, forget this line integral stuff for a minute, okay? I talk about work is force times displacement. But when the force vector points at an angle relative to the displacement, you only consider the component parallel to the displacement. Plain English. Pulling a child in a wagon. The handle is usually at an angle, say 30 degrees above the horizontal. Yet when you pull the child, they move along the sidewalk. So to calculate the work you do, you take force parallel in the x direction or in the horizontal direction only times the displacement. In math class, you call that a dot product. How much of one vector, vector A, is in the direction of vector B? That is on the AP Physics equation sheet. It's, the dot product A dot B is A times B times the cosine of the angle between them. When we take what is called a line integral, that's what we're doing. We're saying how much of this vector is in the direction of that vector. In this case, how much of B is in the direction of delta S, right here. The way that reads is we would say B dot ds. And if we want to add up, right, so here it would be B times delta S times the cos of the angle. And we do that for every chunk. Now, when the path looks like this and the magnetic field looks like that, It's impossible to do that line integral. You would need to know some kind of mathematical function there, okay? And I just don't have that in this slide. Hey, folks, no biggie, because we're going to see it gets way easier. Let's just think, though, why would the author choose this? Well, for the path, just because they're trying to give us a general sense of an idea of path. And why would we choose the magnetic field to look like this? Imagine I put a bar magnet right here. North pole here, South pole here. This is the magnetic field that would be produced by that bar magnet. So that doesn't seem too crazy. Now, in practice, look at how easy it's going to be. Here, no matter where I look along that path, absolutely none of the magnetic field is parallel to the path. So when I take the sum of all those little dot products, B dot ds, the answer is 0. Here, this magnetic field plays extremely nice with the path I've chosen, because no matter where I look along the path, the field is parallel to the path here, right where it touches, right there. This field is parallel to the path. Right here, where this field vector touches, it's parallel to the path. So I don't have to take cos theta. For every little line integral that would make up the total line integral, it's just going to be b dot ds. So the sum there would be the intensity of the magnetic field that looks like it stays uniform times the total length of the path. Now, how do we use it not for generic paths like this, but for a something we might see in magnetism? Well, it just so happens that when I have a current carrying wire like this, and I use the right-hand rule for fields, I see that I know that the field around this wire is nice and clockwise. Okay. Let me enclose. This is now where it gets kind of like Gauss's law. In Gauss's law, you take an imaginary surface through which the flux, the electric flux, punches. Now, to punch through a surface for electric fields, the field and the surface need to be perpendicular. But for magnetic fields, right? For magnetic fields, we look for the field and the imaginary line we choose to be parallel. Okay? Let's now think about, there we go. Let's think about the line integral b dot dl for this path. Let's come over here. I'm interested in the line integral of b around this circular path. Now, if you look, start and finish, that's not a generic line with a start and a finish. It actually starts and finishes here. So that line is a closed loop. And so that's what this little symbol on the integral means, is that it is a closed loop. It's still a line integral. It's just along the line integral around a closed loop. Let's see what that would equal. Well, it would equal b times the total length of this circular path, which would be the circumference, 2 pi times the radius. Careful here, that's not d diameter, that's actually this distance, which is the radius. So this makes sense. The integral b dot ds is b times 2 pi d. Now we already know from the last lecture that the magnetic field this distance away is mu naught I over 2 pi d. So take this line of algebra and come down here. The line integral b dot ds equals this. But don't forget b is this. So substitute this disaster into here, and we get on the left-hand side integral b dot ds. And when you do the algebra with all this crap substituted into here, the right-hand side is just mu naught I. And that is humongous. And that right here is what we call Ampere's law. when you enclose current, okay, the line integral around that current, enclosed current, is going to equal nothing more than mu naught I. Now, it would be tough to figure out the path of the line integral around this weird path. So the paths we will choose will be just like Gauss's law. There will be symmetry with respect to the current carrying wires, okay? We'll either go with a circle or a square or a rectangle, depending on what the geometry of the situation entails. And wait, can we do like geometry like this where we have multiple wires and stuff? Oh my gosh, this looks scary. Hey, lock into this. Ampere's law. Integral B dot ds equals mu naught I enclosed. Just like Gauss's law, charge enclosed. If there was any other extraneous charge that wasn't enclosed, it doesn't count, folks. Ignore it. Same thing with current. Current enclosed. Let's see what that looks like. They're telling us what the line integral is. It's mu naught I enclosed. And they're telling us that it's mu naught times 7. Okay? So, what's current 3? Right? We couldn't really compute the line integral B dot dl here, but we know it equals mu naught I enclosed. So if they're telling me I enclosed is 7, you tell me. I3 has got to be 1 amp opposite direction of I2. So 1 amp in. Done. Okay. Integral of B dot ds here would be mu naught I enclosed. So what would be the I enclosed? Well, I've got current 1 up, current 1 down. So, let's talk though. So I know it's going to be the difference. Is it going to be 1 minus 2 or 2 minus 1? Well, which wire would have direction in the direction of the path that I'm using? Here's my path. This is not a field. This is a path. So what wire makes a field that is in the same direction of the path? Do the right-hand rule. I think it's wire 1. So wire 1 would be aligning with the path and wire 2 would be fighting it. So I'm going to say 1 minus 2. Done. That's it. Okay. The examples basically are going to fall out of the Ampere's law problem set, and this has gone on long enough, so we'll stop it there, and we'll do some kind of walkthrough at some point and do that. So, all right, hope this helps.